Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Tavarico, and with me as the presenter we have Mr. Peter Stones and Mr. Per-Åke Bjornstedt as well for technical support. I'm pleased to announce here the 5th presentation of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Teams live event. The 5th presentation of the program will be the one starting in few seconds with the title, What do you know about corrosion and welding? We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find in the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. So that said, and now let's start the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. It's my pleasure to be here presenting the monthly live event. A couple of things. We intend to, as Clemente said, to present for about 30 minutes, so not too much, but there's an awful lot of information in here. I obviously cannot go into too much detail because of the 30 minutes, so we're more than happy to supply you with copies of the slides if you request them. Both Clemente's and my contact details are on the last slide. We're more than happy, just drop us an email and we can send you the slides, so you don't have to make notes. Please use the Q&A box on the screen and we'll do our best for 10-15 minutes afterwards to answer any questions that we've got outstanding, or please feel free to contact us anytime afterwards. Okay, so corrosion is a very difficult subject, and it's because there's an infinite number of variants on it. The environment that the metal is operating in, the temperature, the pressure, everything has an effect on the rate of corrosion. So in order to have a table, for example, for every single eventuality is quite impossible. So really what we have to do is a few tests for the biggest events, and then interpret these results. The best thing you could possibly do is actually do some physical testing. So make a mock-up of the metals and the environment, and do some measuring, do some testing yourself. So what is corrosion? It originates from the Latin word corrodere, meaning gnaw away, and it's defined as a dissolution of material due to a reaction of the surrounding environment. So rust is a common one that we used to see a lot on cars, not so much these days. That's the electrochemical erosion of iron. Erosion is a way that corrodes metals away, but it's not only metals. Ceramics and polymers also suffer from corrosion, for example. So it's a very natural process in that the metals that we use all start off in the ground as an ore. So essentially they're at low energy down here. What we do is put energy into them to create steels and alloys. So something like a steel, high strength steel or a stainless steel contains a lot of energy. All that wants to do is lose that energy to return back to what it was, essentially. And what corrosion does is make that happen at a greater or a lesser rate. It wants to return, it wants to go from high energy to low energy, as does everything. So what's so important about knowing about corrosion? So obviously the products that you're using, the applications that they're designed for, it's very, very relevant to know what the effect of corrosion will be. So in terms of designing your products, the applications it's going in, the process that it's going into, and obviously it can be a useful marketing tool. If you've got an alloy that's better than somebody else's, for example, then it's a winner, and corrosion results are a big part of that, especially when we're talking about things like stainless steel and nickel alloys. So the different types of corrosion that I'm going to be talking about, what's known as wet corrosion, because they all need a liquid to make them happen, and electrolytes. So general corrosion, intergranular, pitting or crevice corrosion, stress corrosion, and galvanic. Okay. And an interesting slide, this is from a few years ago, but it's real data. 954 cases of failure for 304L stainless. So out of those 954, 38% of those were stress corrosion cracking. That was the reason for the failure. 25% was pitting. So by far, general corrosion, pitting, stress corrosion is by far the biggest cause of corrosion failure on that 304 stainless. Interesting figures. So moving on to general corrosion, this is iron oxide. It's the red rust that you see on a car, on an iron bar, on an old gate. The thing about general corrosion is that it operates at the same rate all over the surface. So what happens is that the iron in the steel, or the iron, oxidizes. So it reacts with oxygen. The reaction's increased if the iron is submersed in water, but it happens on all the surface at the same rate and all over the surface. So it's very, very predictable. It's very relatively slow, but it can be increased with the acidity of the rain, for example, or temperatures. And because it's very predictable, you can design with that in mind. For example, we've got general corrosion. This is stainless steels, but it's still general corrosion. You can see different types of stainless steel in this picture dipped in sulfuric acid. So it is a general corrosion that's happening on every surface of the steel. In order to test it, and most corrosion tests basically operate in the same way. You'll start off with a known specimen with a known weight very accurately, and then submerse the piece, the test piece, in a boiling acid, some kind of nasty corrosive solution for a test period, 24, 72 hours, whatever. After that period, weigh the piece very accurately, and then you've got a perfectly predictable rate of wear, rate of corrosion on that part. You can extrapolate the weight on the surface area of the component, and so you'll know in terms of, say, millimeters per year how much wear that is going. So the result of that kind of testing produces these things called ISO corrosion diagrams. Now, it's a bit wordy and maybe a little bit complicated, but it's necessary to understand if ever you're talking about corrosion, because these things exist for an awful lot of alloys and an awful lot of corrosive environments. So this is specifically for hydrochloric acid. Along the x-axis, we've got the percentage strength, if you like, the weight of the hydrochloric acid. And up the y-axis, we've got temperature. So this is for a rate of 0.1 millimeters per year. So something like a 316 at 1% hydrochloric at 40 degrees. That's the point where, so at 40 degrees at 1%, it will corrode at 0.1 millimeters per year. Something like a super duplex, so a 25% chrome super duplex, this doesn't even start to corrode at 1% hydrochloric, for example. So if you're designing something in super duplex and it's in a hydrochloric acid environment, then you can tell from this chart how long your component's going to last. This is the basis. The ISO corrosion diagrams are the basis of most of the empirical testing, and the information's freely available. The problem is, if you don't have exactly the alloy that you're using, there's no graph for that, or there's no graph for the corrosive media that the part's going to be submitted to. Moving on to pitting corrosion, this is quite a nasty corrosion. It's a local corrosion that starts in a very discrete area of the surface. So for say a stainless steel, you have a passive oxide layer. So anything that contains more than 12% chromium The chromium in that will react with oxygen in air and create chromium oxide. So it's a very, very thin. This diagram makes it look like it's about 5 millimeters. Well, it's microns thick. It's a very, very thin layer, but it's enough to make it stainless. So that's what makes a stainless steel stainless. That's what helps. What happens with pitting corrosion is when that passive layer is broken. So it's been damaged for some reason. This could be mechanical damage, grinding sparks, whatever reason. If that pit is then allowed in the open again, it's left in air, then the chrome oxide will reform. It kind of heals itself, and that's fine. There'll be no corrosion. If, however, that area is now the damaged passive oxide layer is subject, is put under some kind of liquid. Chloride-bearing liquids are worse, but even rainwater will mean that no oxygen can get into that surface. And what happens is basically there's no oxygen in here, so the oxide can't reform. And then what happens is that the pit turns into the cathode, the metal turns into an anode, and you get an electrolytic reaction that starts to eat away and create a pit. So on the surface, the damage doesn't look too bad, but underneath, a bit like an iceberg, it's much bigger damage. This is it's not really predictable. It's not readily predictable. It's not like general corrosion. So it's quite nasty, and the failures will be very sudden. Now, the resistance to pittings is increased by increasing the alloy content of the steel. So with more chrome, molybdenum, tungsten, niobium, for example, you can increase the pitting resistance, and we'll go and explain that a little bit later. And I also go on to explain the testing for it as well. So it's a surface defect that acts as the initiation point. Chloride concentration makes it work faster. The lack of oxygen contributes, and the flow of the liquid. If you increase the flow, then it will increase the corrosion. Now, this thing called the critical pitting temperature, we want to find out when this particular material starts to pit, at what temperature. So we use this thing, ASTM G48 testing, a fairly common testing, corrosion tests for stainless steel and nickel alloys. There are various types, various different methods, and dependent upon the type of metal, so austenitic stainless steels use one method, nickel alloys use a different one, for example. But method E is used to determine the critical pitting temperature. And this is, again, it's weigh the specimen, submerge it in this nasty ferric chloride at a starting temperature, whatever that may be. After 24 hours, weigh it again. If the weight loss is less than a 10,000th of a gram, then there has been no pitting. You've increased the temperature by 5 degrees and repeat the test. When it starts to pit, when the weight loss is greater than that figure, then it's started to pit. That would be the critical pitting temperature. It's not expressed in terms of a corrosion rate, in terms of millimeters per year, but there is a scale. This pitting resistance equivalent, the PRE number, is a scale that we use to rank materials on how resistant that they are to pitting. And it's based purely on the composition of the metal. So the more chrome, the more molybdenum, the more nitrogen, the bigger this number. The bigger the number, the more resistant that metal is to pitting. To give you some idea of the scale, a 316L austenitic stainless steel has a PRE number of 24, whereas something like a super duplex, 25% chrome super duplex, has a PRE number of 42.5. Looking at this illustration, excuse me, this illustration shows basically that information. So these samples, test samples of various grades of stainless steel, have been submersed in this ferric chloride at 80 degrees. The 316L with a pitting resistance of 24 is quite badly damaged and pitted, whereas the super duplex doesn't look to be touched. Just a note about duplexers. Duplexers consist of two phases, austenite and ferrite. That's why it's called duplex. It's very important in the manufacture that the manufacturers of the steel need to ensure that even though the ferrite and the austenite phases have different compositions, that the PRE is exactly the same. If it's the same, then it will wear at the same rate. If you have a differential PRE number between the ferrite and the austenite, then you'll get localized corrosion. You'll get corrosion of one of the phases. In real life, that's what it looks like. Underneath the surface, you can see there's a big hole. So on the surface, we're looking at dots, at pits. But if you section those, then you'd be seeing big holes. So obviously, if there's sufficient damage done to the integrity of the metal, then it will fail. Crevice corrosion works by the same mechanism as pitting corrosion, in that it's a damage to the passive layer on the surface, but it's done usually by design. So something like a tube sheet or a flange. The action's exactly the same, that you're damaging the passive layer, basically submersing it in a liquid, some type of electrolyte, and covering it up, taking the oxygen out of it. This is a tube sheet, example of a tube sheet where the tubes have been pushed through the end of a tube sheet. So obviously the ends there have been damaged, mechanical damage, by virtue of them being pressed into the tube sheet. And after only 3 months in seawater, we've got this corrosion happening. And basically, yeah, it can be avoided by design. Things like an overlapping weld, you've got a very strong crevice zone in here. So the chances are that passive surface has been damaged. If this joint is then not allowed to repassivate and is submersed in water, then you're going to get crevice corrosion. On a gasket, around gaskets is where damage has happened. You're trapping, if you're trapping moisture in there, that'll happen as well. And again, at the end of tube sheets, or within tube sheets, if you weld around them, then there's no crevice. If you don't, then there is a potential. And the test for that is basically the same. It's a G48 corrosion test, but you're actually creating a crevice by this crevice former, which is a flange with a nut and bolt. So the whole lot is submersed underwater. So you're trying to generate a crevice. And by exactly the same method, you'll generate the crevice temperature. Stress corrosion cracking requires on several things to happen. So it's very popular, I should say, very common in the petrochemical industry, because it really requires chloride solutions. So oil containing pipelines, for example. It's very unpredictable and it's a very rapid failure, and you can see the crack goes through and along the grains, and it initiates in a pit. So if you have a material that's liable to pitting corrosion, if that component is starting to be corroded by the mechanism of pitting corrosion, and these other three things, it's under a high temperature, which is higher temperature, it can only be 60 degrees, for example, the component's under stress, and it's in a chloride solution, then all of those things combined make it very, very liable to stress corrosion cracking. So it requires, as I said, it requires three things. It requires it to be under a strain in a corrosive environment and at an elevated temperature, and it initiates at a pit. So for chloride environments, duplex are the materials of choice. They last a lot better. And temperatures usually above 60 degrees again. And the thing about the stress is that although the component may not be designed to be stressed in service, the way that it's been fabricated may have put some residual stress into the component. And that can catch you out. If heat treatment and cooling has not been done correctly, then you can put thermal stresses in there. If the part's been formed, for example, and not stress relieved, then there are stresses already in there, and that's the kind of thing that in the past has caught people out. Here's a photograph of a weld between duplex and 304 stainless, and you can see the duplex is quite impervious to chloride corrosion. The 304 is not, and you've got a very good example there of the stress corrosion going along the grains and through the grains. In terms of stress corrosion cracking resistance, exactly the same process again for submitting the component to the relevant parameters at temperature, and you come out with a diagram like this, a graph again. So this is done completely empirically, and what this is showing again, so you've got 304, 316 stainless here, can only cope with a chloride weight of less than 0.1%. Anything bigger than that, it will crack, and below 50 degrees. Whereas at the other end of the scale, we've got 2507 super duplex stainless steel. There's no cracking at all, even at elevated temperatures and something up to 1% chlorides. So as I said, the testing is basically the G48 test, but with an addition of strain in there as well. There's some kind of stress put onto it, so it can either be as a bend test or as actual tensile test. Granular is due to carbide precipitation. So because of the nature, the components within the stainless steel, it's a phenomena, it's a reaction that occurs between these temperatures, 500 to 900. So that means that the heat affected zone are the areas that are most prone. So the carbides, nitrides, intermetallic phases, they precipitate, they grow at these grain boundaries. So the carbides are generally chromium carbides. So that means that the chromium is leaching out of the adjacent grains and going into the grain boundaries. What happens is that the grain boundaries are very rich in chromium, and the adjacent areas can have less than 12% chromium. So it's subject to a corrosive attack. If it's got less than 12%, it's not a stainless steel anymore. As an illustration here, so these are three grains rather, with the grain boundary in between them. So the grain is chromium rich. These areas immediately adjacent to it are chromium depleted. Okay, so the carbides can come from oil and grease on the surface, dirt on the surface, a high carbon content of the steel, for example. And again, if the heat treatment's been done incorrectly. Taking a cross section across a grain boundary, we've got an 18% chrome content grain. Okay, the grain boundary where all the chromium carbides have been precipitated. So this is very chrome rich. It's above 24% at the grain boundary. So you're talking microscopic level, but at the grain boundary, the chromium content is very high. But that means the area immediately adjacent is very low. And on this graph, it's showing it down to be about 3%. At 3%, there's no corrosion resistance at all. So it's subject to intergranular attack. So what do we do? Use low carbon content base materials, low carbon content filler metals such as 316L, L meaning low carbon, 308L for low carbon. You can use niobium stabilized alloys as well. The niobium basically pins the grain boundaries. Full solution anneal if it's possible, and if you allow the material to dwell between these temperatures, then that's when you're going to be susceptible to intergranular corrosion. So anything you can do to avoid that will help. Heat treatment, welding. Follow the guidelines. The methods for testing intergranular corrosion, it's this ASTM A262, for example. So the buzzwords, things like Huey, Strauss, and Stryker, are 3 different methods for testing intergranular corrosion. They're slightly different, and depending upon which alloy that you want to test is which one that you would use. But there would be the buzzwords to look out for. Finally, the last one I want to talk about is galvanic corrosion. So this is where we get 2 metals in contact with an electrolyte. So the metals are graded on a galvanic scale or a noble scale as being more noble or more reactive. If the difference between the 2 is large enough, then a reaction occurs. So on the galvanic series, something like magnesium is very reactive. So that will start to fizz immediately that you put it in any kind of acid, whereas gold at the other end of the scale wouldn't. So the bigger the difference between 2 materials here, the more reaction will happen. And it's with an electrolyte in between, which can be water, seawater, whatever. It's the basis on how a battery works. A wet cell battery is exactly this kind of process. Once the reaction has started to happen, then the more reactive metal will start to corrode even quicker, and the more noble one will corrode less. Why should we worry about this? Well, something like stainless steel bolts in on a mild steel frame underwater, for example. So there's a big difference, there's a big potential difference already set up between the 2, and you'll start to get this galvanic corrosion. What can we do about it? Avoid at design stage, but there's a whole business involved in these things called sacrificial anodes. So these are magnesium, zinc, aluminium, big business, where you fasten large blocks of these onto, these are the legs of a platform that would be submersed in the sea. What you don't want to happen is for the metal in the construction to start eroding. What you want to happen is for the potential difference to start eroding the sacrificial anode. Okay. We have a summary table that I don't propose to read out, but you can look on the if you get copies of the slides. But we've just got a quick table on prevention for all the various types of corrosion that we've discussed. So I hope you found that interesting. Thanks for taking part. I think I'm just about up. My time is just about up. As I say, please, if you wish to contact us, feel free, and we're happy to give the copies of the presentation out. Myself and Clemente's details are on the screen there.